Welcome everyone to my course Formal Methods for System Verification. In today's class, we will learn the binary decision diagram. So, what is binary decision diagram? It is effectively a acyclic graph or DAG in which through which I can represent any Boolean function or even a combinational circuit. Okay. So, where each nodes represent one variable and it has also two leaf node which is called terminal nodes which has 0 and 1, right. So, effectively what I am saying is that if you have a function of say x, y and z, I will have a node on say x, and then what I am saying, it will have two outgoing edge, one is called 0 edge and one is 1 edge. So, say this is my 0 edge, this is 1 edge, right. So, this is 0 and 1, and then we will have the node corresponding to y and z. Let us say I have put y here, and again I will have 0 and 1 node, right, 0 and 1, and let us say I put z here, again I will have 0 node and 1 node, 0 node, 0 usually given by dot, and this may reach to 0 and 1 based on the functionality, right. So, if say this is a function of x and y and z, so this will be 0. So, it is basically 0, 0, 1, then 0, 0, 0, 1, 0, this is also 0. If I put 0, 1, 1, this is also 0, right. Now, x equal to 1, I can choose any variable here, right. So, that is 0, then it is 0 and 1, then I will have y. So, 0 node 1 node, 0 node 1 node, right. So, 0 1, 0 1, 0 1, and you know that only if all of them is 1, then only 1, rest of the node are 0. So, this is kind of a BDD of the function this. Okay. So, this is a acyclic graph because there is no cycle here, and it is a directed graph. Usually these edges are directed. Each node represent the variables, and every node has two outgoing edges, one is with 0, one is with 1, and the terminal nodes are 0 and 1. Okay. This is by definition binary decision diagram. Okay. So, if you see here, this is one more example, the similar example for A and B. So, here if A equal to 0, I can directly decide that I do not need to check B, and if this is little bit optimized version, right. So, now if A equal to 1, then B equal to 1, this is 1, and if it is A 1, B 0, then it is 0. This is the BDD of this. Here I have not considered B here, because in both cases I am going to get 0 only, right. Okay. Now, essentially if you see this, this is nothing but a truth table, right, because you are representing all possible values of your function, that there are x, y, z. It is effectively if you consider these paths, there are actually 8 paths, right. So, this is basically 2 to the power n possible paths you are representing, which is nothing but truth table, right. This is yet another way of representing the truth table. So, there is no fun there, right. So, if you are already representing the circuit truth table as a binary decision diagram, it does not add much value, because it is always an exponential. But the value comes from two other version of the BDD, which is basically called ordered BDD, and then finally what is called a reduced order BDD. So, finally people talk BDD equivalent to the RO BDD, reduced order BDD, and this is a very important data structure because it has some unique property. Why? It basically say canonical representation. Okay. What does it mean? Canonical means is unique representation. Okay. So, it means if there are two functions which expression may be different, but if you construct their RO BDD, this will be always same, right. You think about an example, very simple example, say you have x dot y plus z, right. You construct the RO BDD, and you have say x y plus y z. These are actually same, right. You construct the RO BDD, you will get these are same, right. I am just taking a very simple example, but you think about a very big example. You have a very big circuit of thousands of gates, this has 100 of gates, you can still construct the RO BDD, and they will be, if they are equivalent, they have the same RO BDD. right. So, this is the kind of advantage of ROBDD, which is canonical representation. So, this has very wide use in the circuit optimization, then formal verification, in model checking, SAT solver, everywhere, right. So, this is a very important data structure and we must learn as a formal methods course. Okay. So, effectively, although I have introduced what is BDD, logically is a DAG, but finally, we will see how we can get the ROBDD. Okay. So, that with example I will show you. Let us take this function. Let us say I have the function which is x1 and x2, not of x1 and x3, right. So, if we construct the BDD, you will get this. Okay. So, this is x2. Few terminology you should know of. For example, this if you think about this, every node has some name, right. This is the node V4, this is V5, this is V6, this is V7 and so on. So, if I say the left, right, the var of V2, it is basically x2, right. So, the variable associated to the node, right, this is var. Then left of V2, which is basically V4, right, right of right is the right one, V2, which is basically V5 and so on. So, every node you can also think about the root of this BDD is basically is x1, right. So, you can think about variable corresponding to this node, left, right and root, right, these are the common thing. So, what I was talking about the order BDD, how it is different. You see here, when I construct the BDD of this x, y, z, what I say that in this path I consider x followed by y, then followed by z. In this path I consider x followed by z followed by y. So, the order is different, right. In different path you have a different variable order. In order BDD I say ki no, you consider a specific order, right. If you consider x, y, z is the order, x followed by y followed by z, in all path you should follow this, which is not the case here, right. So, in a order BDD, that is the only advantage change we are making from the normal BDD definition is that you maintain the variable order in all path. Okay. So, the example I have taken here, it is basically that, right. So, you have x1 here, x2 here, x3 here, x1, x2, x3. So, if you consider order BDD, now there are some interesting things. So, each level represents a variable, right. So, this level, so this is level 1, this is level 2, this is level 3. In level 1 it is x1, right. All nodes in level 2 is x2, because this level 2 is now representing the x2 variables. Level 3 all variable is x3, because I have considered the order x1, x2 and x3. If I consider a different order, say for example x3, x2, x1, then level 1 would have been x3, then level 2 is x2, level 3 is x1, right. So, this variable order is important and practically we do not consider any BDD of this kind of thing, right. This is useless. So, we always consider order BDD, where I mentioned that each level represent a particular variable. So, if say for I will talk about that, say let us say this variable does not occur, then I will just keep it and I will put x3 here. So, every level has one level represent one variable. So, this is what order BDD. Okay. And then what is reduced order BDD? We found that this, when you construct this, is basically truth table, which has no use in practice, but we can identify all the redundancy in this diagram and I remove them, right. So, if you identify all the redundancies and remove them, I will get the reduced order BDD, and that is the unique one, right. So, we will see how we can reduce the redundancies. Okay. So, there are 3 rules effectively. The first rule is very obvious, that I am putting so many 0 and 1, I do not need to put that, I can put only 1 0 node, 1 1 node. Okay. So, that is the first reduction, that you basically merge all the leaf nodes into 1 0 node and 1 1 node. This is very obvious. So, what will happen effectively? I will put only 1 0. So, whenever all the edges are going to the 0 node, that will come to this 0 node, all the edges going to the 1 node, that will go to that 1 node. It is very simple, and the version will look like this. Okay. So, here, so all the 0 nodes are coming here and all the 1 nodes are coming to this. We usually represent the 0 by dotted nodes, but here this you can consider 0 node, but that does not matter much. Okay. So, we have now this. Now, can you see? So, this is the rule 1, it is very obvious rule. Can you see some redundancies? So, we can see some redundancies here, right. So, for example, you consider this particular case, its left edge and the right edge is going to the same successor node, right. So, what that means, this node is redundant, right. Similarly, this case is also the same thing, that whether the value of x 3 is 0 or 1, it will always become, output will be 0. So, I do not need this node, right. So, this is my rule 2. Whenever I have such a node where the left and right child point to the same node, this node is redundant. So, I will remove this, I will remove this. Okay. But what I will do now? What I will do? The incoming edge to this node I will connect to the successor node. So, what effectively I will do? I will put x 1, then x 2, and then I have 0 and 1. So, x 2 0, it is going to 0. So, if it is 0, I will go to 0. X 2 is 1, it is going to this node and which is basically 1. So, I will connect directly to 1 node, and other part I am not touching, because there is no redundancy here, right. So, here you have x 2, this is x 2. So, this is 0, then you have x 3 and x 3. So, if you get 0, you will come here, if you come 1 here, and then you have 0 1, then 0 1, right. So, this is the optimization 2. Okay. So, I will find out, is there any node redundant. If the left of that node and right of that node is same, that means they are pointing to the same successor node. So, I will basically, what I will do, the predecessor of this node, I will connect to the successor of the node of phi. Right? That is what I have done effectively. The predecessor of this node is this, successor of this node is this. So, I connect the predecessor directly to the successor. So, this is the BDD I obtained here. So, this is I got. Now, can you see any other redundancy in this particular graph? So, I can see one. You think about this particular graph. What is happening here? Whenever x 3 I got to 0, and if x 3 is 1, I got to 1. And think about this one, right. It has the same behavior. Whenever x 3 is 0, I am going to 0. Whenever x 3 is 1, I am going to 1. Right. So, what is basically means, this called isomorphic subgraph. So, there are two subgraph which has the same root node, that means it has the same x 3 as the variable, and they are left and right going to the same successor nodes, right. So, this can be 0 1 or it can be some other node also. Effectively, they are actually the exactly same graph. So, I can remove one of them, right, and I can only keep one of them. So, let us say I remove this, then what will happen? Whatever the predecessor edge is connecting now, I will connect here, because I am going to remove this, I will just keep it one of them, because I do not need both of them, they are basically same. Then what will happen? The modified graph will be like this, x 1, x 2, and here x 2, this is 0. Then I just keep 1 x 3, and whether it is a value of 1 or 0, I will go to this x 3, because the rest of the things are same. And what I will do, I just keep one of them, right, 0 and 1, and here also 0 and 1. So, this is the modified version of the BDD. So, this is the rule 3, merge isomorphic subtrees. So, how do I define two tree T1, T2 are isomorphic if their root node have the same variable? You remember this must be x 3, it should not be x 3 and x 2. So, they have the same root node, and left and right child point to the same node, right. Basically, the left of the root node and left of the root node of T2 are same, right of the root node of T1 and right of the root node 2 is the same, right. So, exactly the same thing I have shown there. In this case, what I will do, I will basically remove one of them, okay, and make the connections. So, this is what the graph that I construct here. I just show it very clearly here. Okay. So, this is after merging the isomorphic subtrees. You can see clearly again there is some redundancy, and I can apply rule 2. So, what I can do, I can remove this node x 2, right, and what I will get effectively x 1, and then if I remove this, what will happen, this predecessor will come directly to this, right. So, I have x 2, x 3, and you have 0 1. Right. So, basically if it is 1, I will come here, if it is 0, I will come here, and if it is 0, I will go here 1 1, and the same thing here 0 and 1. So, this is the final BDD after removal of this, right. So, this is the final BDD, I got it. So, you see initially the graph has 1, 2, 3, 7 nodes, and 7 plus I can say 8 plus 8 15 nodes, right, including the leaf nodes. Now, I have effectively the final BDD has 1, 2, 3 nodes and 2 leaf nodes, 5 nodes, 15 to 5, this is the reduction, right. So, and no further optimization is possible. So, this is my ROBDD. So, this is the ROBDD of that function, okay, and this is unique. Okay. You see note here, this because I have considered the order x1, x2 and x3, although there is no x2 occurred here, I keep this x3 in the next level, because each level represent one variable. So, since x2 does not occur here, I just keep it blank, but I maintain a different level for x3. Okay. This is the protocol we usually follow. Okay. So, this is great, right. So, once you have the original function, you effectively can think about considering the original BDD, and then you apply this 3 rule iteratively, and you reach to a BDD where no further optimization is possible, and that is your ROBDD. Okay. So, this is good. So, I will now quickly show you the some application of ROBDD. The first thing I will talk about say satisfiability. So, as I mentioned, it can be used in satisfiability checking, equivalence checking, logic optimization, model checking and so on. So, I will just give you these brief examples. Okay. So, what about the satisfiability checking in BDD? You think about this, whether, so this is corresponding to the function x1 and x2 or not of x1 and x3, right. This is a function, right. So, we started with this function, right, not of x1, x3. So, if I just try to check whether this formula is satisfiable or not, right. We have already discussed the SAT solvers. We can actually convert this into CNF. This is by the way in DNF. We can convert this into CNF and check whether the formula is SAT or not, right. But what about the satisfiability here? It is if this node exists, right, that means this formula is satisfiable, because there is a path to this one. So, it means what? If x1 equal to 1 or true, x2 equal to true and x3 does not matter, it may be false or something, I will basically get true, right. So, this is my SAT formula, right, let us say this. So, this is my SAT formula here. So, checking satisfiability in a ROBDD is constant time, because what you have to just check? You have to just check whether the node with 1 exists, terminal node 1 exists, that means it has not been removed by any optimization, and hence this is SAT. And to get the assignment, you have to just do a DFS from here, and whatever the value we will get here, that is basically the height of the tree, which is n. So, order of n, right, you will get the assignment also. On the other hand, you have seen that in SAT solver it can be NP complete, right, 2 to the power n, right. So, you might get confused now that does it mean that you solve the NP complete problem in polynomial time? The answer is no. In subsequent classes, we will see that the size of the ROBDD is very much sensitive to the variable ordering. Okay. So, if you have take a good ordering, you get a good BDD, and you can actually get your satisfiability in very order of n time, right. But if you take a bad ordering, your size of the BDD will be exponential. So, the construction of the BDD will take exponential time itself. So, the satisfiability may be polynomial time, but construction itself taking exponential time. So, overall time is exponential, right. And unfortunately, given a formula, you do not know which is a good order, right. So, identifying the good order for which the ROBDD size will be minimum is NP complete problem. So, effectively it is back to square one, right. Your original SAT problem was NP complete, but we have shown that if you have a good BDD, checking will be order of n, right. Yes, no checking is constant 1 and getting the assignment is order of n. On the other hand, constructing the ROBDD is taking exponential time, right. So, and I do not know for which order you get the good BDD, ROBDD, right. So, that is why you may get stuck itself in the construction itself, right, because you cannot determine which is the good variable order for certain functions. Okay. So, that is why it is not solving the problem in polynomial time satisfiability problem, but if you can construct the ROBDD, checking is pretty easy, you do not need any algorithm, DPLL, no algorithm is needed. Okay. Let me give you some funny fact. Think about, I have a formula which is valid, What does it mean? Valid means is basically true for all possible input. Think about a function I just saw here with x1 and x2, and it is basically all path leads to 1. You see, whatever the value of x1 and x2, it is always lead to say 1. So, in this case, if I try to apply the rule, right. So, I will basically combine this into a single node, and then this will not become redundant, because if you combine this to a single node, this node become redundant. Similarly, if you combine this to a single node, this will be redundant, and then if you remove this, you will effectively end up getting a single node, right. You will get basically this node, and after that you will get this. So, you basically for a valid formula, ROBD will have single node of 1, right. Similarly, if a formula is unsatisfiable, I will get a single node with node 0, right. So, unsatisfiable formula, if you keep applying the ROBD reduction, you will end up getting a single node of 0. So, then I will say the formula is unsatisfiable. So, checking of satisfiability using ROBD is pretty easy, but problem lies in the construction of a good ROBD or identifying the good variable order for which I get a good ROBD. Okay. Now, think about equivalence checking problem. So, you have one circuit, right, and you have another circuit. This is say F1 and this is F2, and remember they have same variables, otherwise you cannot come checking equivalence, right. So, they are, if you have x, y, z here, you would also have x, y, z, right. What I can do, I can construct the ROBD from here, I will construct the ROBD from here, and what I say, because ROBD is canonical representation, so they should be the same if they are equivalent, right. So, what I effectively do, I will construct the ROBD, I will check whether I got the same ROBD from them or not. If I get the same ROBD, these two are equivalent. You remember when I was talking about this equivalence checking, I construct this formula, I construct this formula, and then I just check sat of F1 not equal to F2, right. And if I get this formula is satisfiable, that means there is an input for which this formula output is different. So, they are not equivalent. And if I get unset here, it means the formula, there is no input for which the formula is not equivalent, hence it implies the formulas are equivalent, right. So, again you need a complete satisfiability checking. Here is just construction of the ROBD and check whether they are same or not. So, it is very easy, right, checking equivalence with ROBD. There are also other applications in the Boolean circuit optimization. You think about, I have a very big circuit, right, a very big circuit, and there may be some part of this circuit and this part of the circuits are actually equivalent. If they are equivalent, what I can do, I can just remove one of them, right, because they are calculating the same output. But how do I identify the equivalent sub circuit? Again the same idea, you basically take a subgraph here, you take a subgraph and construct the ROBD, and if you see the ROBD are same, they are equivalent, I remove one of them, right. So, this is again is very popular identifying sub circuits within a big circuit, right, and you can actually check whether they are equivalent or not using ROBD construction. Okay. There is also you can do that, you take a very large circuit which is unoptimized, and then you construct the ROBD, it is a very small representation, right. And once you have this ROBD, you can actually construct back a optimal circuit directly from the ROBD. I will show you how. Okay. Let us say the example that I have taken earlier, the ROBD that I have constructed. So, what the ROBD I have constructed is this one, right. So, x1, then if you have x2 and this is x3, 0 and 1, right. This is the ROBD I have constructed. So, if I have this ROBD, how can I get a circuit based on mux? Okay. You can think of that I have a mux multiplexer which is controlled by, so you have one multiplexer which say I am picking 0 and 1. So, this is corresponding to this one, and it is controlled by x3. Okay. Similarly, I have one more mux which represent this x2, right. So, this is controlled by x2 and you have 0 and 1, right. So, this is basically this node, and then I have one more mux corresponding to this one, right. and this is controlled by x1, and it is connected this. So, this is 0 1 0 1, this is 0 and 1, right, and this is your output. You think about that, this is the circuit which is equivalent to this mux. What is happening here? I am saying that if x3 is 0 1, you pick 0 1 based on this x3, then you pick this 0 1 based on this x2, and finally pick between these two value based on the value of x1 0 and 1, right. So, this is the line 0, this is line 1. So, this is the circuit I construct directly from the ROBDD. So, what I can do, I can think about, I have a big unoptimized circuit, I construct this ROBDD, and then I can get a mux level circuit directly from this ROBDD, right. So, this is what we can do in circuit optimization. We can also do the symbolic model checking, which I will going to talk about in much detail in the in subsequent classes where I talk model checking. So, here there is a things called reachability, right, whether you can reach from this state to this state, right. This is called reachability, and we can, what we can do, I can actually model this reachability problem as BDD problem. We can show that you can actually check whether there is you can reach from this state to this state or not by just constructing ROBDD of the states and their transitions. Okay. So, this we will discuss more detail when I talk about model checking. Okay. So, I will conclude with some discussion on this variable ordering. As I mentioned that this variable ordering is the factor that actually determine whether you will get a good reduced order BDD or not. Say I will take some example. Let us say I have taken this example, right. In this case I have already considered the ROBDD. I have shown that there are 3 internal nodes, right, when the order is x1, x2, x3. Whenever I take the order x3, x2 and x1, I will get a BDD with 4 nodes. So, it varies, right, but they are actually the same ROBDD. So, when I am talking about circuit equivalence also, the variable order has to be same in both BDD, then only you can actually get to the same BDD, right. So, similarly, if you think about a function where I am checking whether x1 equivalent to x2 and x2 is equivalent to y2 and xn equivalent to yn, right. So, this is a function. If you try to construct this BDD, there are 2n variables and there are 2 to the power n possible order, right, or factorial 2n order, right. So, if we consider the order x1, y1, x2, y2, xn, yn, right. So, I will basically in the variable I have x1 first, then I have y1, then x2, then y2 and so on. If I consider this order, I get a BDD which has only 3n minus 2 internal nodes. But if I consider the order like first take the x1, x2 to xn and then y1 to yn, I will get a variable where number of nodes are 3 into 2 to the power n minus 1 nodes. Okay. So, it is exponential size. So, this is the order I am talking about. The same function, one order is giving good BDD, another order is giving bad BDD, and the finding the best order is difficult, right. Hence, we are not solving the NP complete problem of satisfactory checking, right. So, I will basically take a dedicated class where I take few functions and say how do you determine which is a good order, which is bad order. Some scenario you can actually identify, some cases you cannot. So, I will talk about more on that in another class. So, before conclusion, I want to raise a questions to you. So, what I am saying here, if you construct the initial BDD, then I have show you the rules to get the ROBDD, right. But that is useless, right, because if you already construct the initial BDD which is unoptimized and exponential size, no matter how do you get the original one, you are already constructing the exponential size. So, this is not so useful, right. So, in practice nobody construct the initial BDD and apply these rules to get the reduced BDD. What I can do, given a function, I can construct the ROBDD directly without constructing the initial truth table type BDD, right, then it will be useful, right. So, in the next class I will explain the method where given a say Boolean circuit or a propositional formula, how can you construct the ROBDD directly from the formula without constructing the initial BDD. Okay. So, that will be the discussion in the next class. Till that time, thank you.